There is something above us that we cannot see. It has no color, no smell, no shape. And yet, it is changing the future of the planet. Carbon dioxide. For more than 2 centuries, humanity has extracted carbon from deep underground, burned it for energy, and released it into the atmosphere. The result is an invisible accumulation. Every year, billions of tons of carbon dioxide enter the atmosphere from human activity. And while forests, oceans, and soils absorb part of it, the rest remains, building up, changing the chemistry of the atmosphere, and warming the planet. Now, a new idea is emerging. What if we could reverse part of the process? What if we could build machines that capture carbon dioxide directly from ordinary air? Not from a smokestack. Not from a factory. But from the atmosphere itself. The concept sounds almost impossible. Because carbon dioxide makes up only a tiny fraction of the air around us. To capture 1 ton of it, a machine must process enormous quantities of atmosphere. And yet, engineers are attempting exactly that. Across the world, new technologies are being developed to capture CO₂ using chemical solvents, solid sorbents, specialized filters, and massive air contacting systems. The vision is extraordinary. A global network of machines, pulling carbon from the sky, transporting it, and locking it away underground. But this raises a much bigger question. Can humanity build carbon removal at a scale large enough to matter? And if we can, will we have enough energy? Enough land? Enough materials? Enough storage? And enough time? This is the story of the race to engineer a new planetary industry. An industry designed not to produce carbon, but to remove it. To understand carbon removal, we first need to understand the problem. For thousands of years, Earth's climate existed within a relatively stable range. Carbon moved continuously between the atmosphere, the oceans, the soil, plants, and geological formations. This natural carbon cycle was never static. But the Industrial Revolution changed the balance. Humanity discovered enormous stores of energy locked inside coal, oil, and natural gas. We learned to extract them, transport them, burn them, and power an industrial civilization. The consequences were enormous. Factories multiplied. Cities expanded. Transportation transformed. Electricity reached billions of people. And global prosperity accelerated. But every ton of fossil carbon burned for energy had somewhere to go. The atmosphere. The concentration of CO₂ increased. And the planet began absorbing the consequences. The scientific response is clear. The first priority is to stop adding more greenhouse gases. That means cleaner electricity, electrification, energy efficiency, low-carbon industry, cleaner transportation, and protecting natural ecosystems. But even if the world reaches net zero emissions, another problem remains. Some emissions are extremely difficult to eliminate completely. Aviation, shipping, cement, certain industrial processes, agriculture, and other activities may continue producing residual emissions. At the same time, the atmosphere already contains the legacy of past emissions. This is where carbon dioxide removal enters the story. The idea is simple. Reduce future emissions, while also removing some CO₂ that is already in the atmosphere. Nature already does this. Forests capture carbon. Soils store it. Oceans absorb it. But natural systems have limits. And they can also be damaged by climate change. So scientists and engineers are exploring another possibility. Industrial carbon removal. Machines designed to imitate one of nature's most fundamental processes, but at an unprecedented scale. Here is the first great engineering challenge. Carbon dioxide is everywhere. But there isn't very much of it. Today's atmosphere contains CO₂ at concentrations measured in parts per million. That means carbon dioxide is a tiny fraction of the air we breathe. Imagine trying to find a small number of needles inside an entire planet-sized haystack. That is essentially the challenge facing direct air capture. A factory capturing CO₂ from a concentrated industrial exhaust stream has an advantage. The carbon dioxide is already concentrated. But direct air capture must start with ordinary atmospheric air. That means enormous volumes of air must move through the system. Fans push air across specially designed materials. The CO₂ sticks to or reacts with those materials. The remaining air passes through. Then the captured CO₂ must be released from the material. And the process begins again. This is where chemistry becomes engineering. And engineering becomes economics. The capture material must work efficiently. The fans must move enormous quantities of air. The regeneration process must consume energy. The equipment must survive for years. And the entire system must operate at a cost society can afford. The technology is not simply about capturing carbon. It is about capturing carbon. Again. And again. And again. For decades. That is the difference between a laboratory experiment and an industry. Today, direct air capture technology is developing along several different pathways. Two of the most important approaches involve liquid solvents and solid sorbents. The first approach uses liquids designed to react with carbon dioxide. Air enters the system. The CO₂ interacts with the chemical solution. And the carbon dioxide becomes separated from the rest of the air. The challenge comes next. The carbon dioxide must be released. That requires energy. The capture material must then be regenerated and used again. The second approach uses solid materials. Imagine enormous structures filled with specialized surfaces. Air flows through them. Carbon dioxide molecules attach to the material. When the material becomes saturated, the system changes conditions. Heat, pressure, vacuum, or a combination of techniques can release the captured CO₂. The material is then ready to capture again. Different companies and research groups are experimenting with different designs. Some systems focus on minimizing energy consumption. Others focus on increasing airflow. Some seek cheaper materials. Others are trying to make the entire system modular. The fundamental problem remains the same. How do you efficiently separate an extremely dilute gas from billions of tons of ordinary air? The answer may not come from a single technology. The future of carbon removal could involve many different approaches. Different climates. Different energy sources. Different geological storage opportunities. Different industrial designs. But all of them face the same fundamental test. Scale. There is a paradox at the heart of direct air capture. To remove carbon from the atmosphere, you need energy. And if that energy comes from fossil fuels, the process could undermine its own purpose. Imagine a carbon removal plant powered by a coal-fired power station. The machine captures carbon. The power station emits carbon. The mathematics quickly becomes complicated. That is why the energy source matters. For direct air capture to deliver meaningful net carbon removal, the energy powering the process must be very low carbon. That could mean renewable electricity, geothermal energy, nuclear power, or other low-carbon energy systems. But energy is not the only challenge. A gigaton-scale carbon removal industry would require enormous infrastructure. Power generation. Factories. Fans. Chemical materials. Pipelines. Transport systems. Storage facilities. Monitoring networks. And maintenance. All operating continuously. Consider the scale. Humanity currently emits tens of billions of tons of CO₂ every year. A future carbon removal system operating at the scale of hundreds of millions or even around 1 billion tons annually would be an enormous industrial undertaking. It would not be a single factory. It would be an entire global industry. And building that industry would itself require resources. Steel. Concrete. Chemicals. Land. Electricity. Water in some designs. And massive capital investment. This creates a critical question. Could carbon removal itself become a significant industrial burden? Or could engineers design systems that remove far more carbon than they emit during construction and operation? The answer will depend on technology, energy, and scale. The word gigaton is difficult to imagine. 1 gigaton is 1 billion tons. To put that into perspective, the world is already dealing with emissions measured in tens of billions of tons every year. So when climate models discuss gigaton-scale carbon removal, they are describing something enormous. Today, direct air capture is nowhere near that level. The industry is still in its early stages. But the ambition is growing. Some climate scenarios envision direct air capture reaching hundreds of millions of tons of CO₂ removal per year by mid-century. In some pathways, the scale approaches a gigaton annually. That is a breathtaking increase. From relatively small demonstration plants to an industry capable of operating at the scale of major global infrastructure. The transition would require an industrial revolution within the industrial revolution. Factories producing capture equipment. Facilities manufacturing sorbents and solvents. Power plants providing low-carbon energy. Networks transporting captured CO₂. And geological formations storing it permanently. The machines would need to operate not for months, but for decades. And the carbon would need to remain underground, potentially for thousands or millions of years. This is why carbon removal is not simply a technology problem. It is an infrastructure problem, an energy problem, an economic problem, a policy problem, and ultimately, a planetary-scale coordination problem. Capturing carbon is only half the story. The other half is storage. Once CO₂ has been separated from the atmosphere, it must go somewhere. One possibility is utilization. Captured carbon can potentially become a feedstock for certain products. Synthetic fuels, chemicals, building materials, and other applications. But utilization is not automatically permanent removal. If the carbon is turned into fuel, and that fuel is eventually burned, the CO₂ returns to the atmosphere. For climate removal, permanence matters. This is where geological storage becomes critical. Deep underground rock formations can potentially store CO₂ for extremely long periods. The captured gas can be compressed, transported, and injected deep beneath the Earth's surface. Over time, geological processes can immobilize the carbon. But storage must be carefully selected. It must be monitored. And it must be managed. A carbon removal system that captures CO₂, only to release it again, has failed its fundamental mission. The goal is not merely to move carbon. The goal is to remove it from the atmosphere. And keep it out. But there is another question. Why build machines when nature already removes carbon? Forests, wetlands, soils, Mangroves, grasslands, and other ecosystems can store enormous quantities of carbon. Protecting and restoring these systems is essential. But nature-based removal also has limitations. Forests can burn. Soils can lose carbon. Droughts can kill vegetation. Climate change itself can weaken natural carbon sinks. And land is limited. The world must balance carbon removal with food production, biodiversity, and human needs. This is why many climate experts see a portfolio approach. Protect existing ecosystems. Restore damaged ecosystems. Reduce emissions rapidly. And develop engineered carbon removal where it can provide additional benefits. The future may not belong to machines alone, or forests alone. It may depend on combining both nature and technology. But there is a danger hidden inside the promise of carbon removal. If humanity believes that machines will eventually clean up the atmosphere, we might delay the harder work of reducing emissions today. This is one of the most important debates surrounding the technology. Carbon removal is not a magic eraser. It cannot justify continuing to burn fossil fuels indefinitely. The physics do not work that way. Every ton of CO₂ avoided today is generally easier and cheaper than removing that ton later. Direct air capture is an additional tool, not a replacement. Its strongest role may be in dealing with emissions that are extremely difficult to eliminate, and in removing some of the carbon already accumulated in the atmosphere. But there is another risk. If carbon removal becomes a massive global industry, who controls it? Who pays for it? Who owns the technology? Where are the storage sites? Who monitors them? And who is responsible if something goes wrong? Carbon removal could become one of the most important climate industries of the 21st century. But it could also become a geopolitical industry. Countries with abundant clean energy may become carbon removal hubs. Countries with suitable geological formations may become storage centers. Companies controlling capture technology could become major players in the global economy. The future of carbon could become a new strategic resource. The central question is no longer whether humans can capture carbon dioxide from the atmosphere. We can. The real question is whether we can do it at the scale required, without creating a new environmental problem. Can the technology become cheaper? Can energy consumption fall? Can low-carbon electricity expand fast enough? Can manufacturing scale? Can carbon storage become globally available? Can governments create credible policies? And can society build the infrastructure required? Before climate damage becomes increasingly difficult to manage, the answers remain uncertain. Direct air capture is still an emerging technology. Costs are evolving. Engineering designs are improving. And large-scale deployment remains ahead of us. But the direction is clear. Humanity is beginning to build machines designed for a task that nature has performed for millions of years: removing carbon from the air. The difference is scale. Nature works across forests, oceans, and ecosystems. Humanity is attempting to build an industrial equivalent. One machine, then 10, then hundreds, perhaps thousands, perhaps more. The ultimate goal is not to create a world where we can pollute without consequences. It is to create a tool that can help repair part of the damage we have already caused. Every molecule of carbon dioxide released into the atmosphere becomes part of Earth's story. Some will be absorbed by oceans, some by forests, some by soils, and some will remain in the atmosphere for a very long time. The climate system remembers. And humanity is now confronting the consequences of 2 centuries of industrialization. The next century will be different. We will have to reduce emissions, protect nature, transform energy, and perhaps Build machines capable of removing carbon from the sky. But the machines will not save us alone. The real solution is not choosing between prevention and removal. It is doing both. Stop adding carbon. And remove what cannot be avoided. The challenge is immense. The economics are uncertain. The engineering is unfinished. And the scale required is almost beyond imagination. But for the first time in history, humanity is attempting something extraordinary. Not simply to change the planet, but to engineer a way to help restore it. The question is no longer, can we capture carbon from the air? We already know the answer. The question is, can we build enough machines? Fast enough? Cleanly enough? And permanently enough? To make a difference, asterisk. Because the future of climate restoration may depend on our answer. Climate restoration. The race to remove carbon from the sky has begun.